Welcome! My name is Megan Lee, and I'm the Laboratory Services Manager here at Avista Technologies. Today, we will be discussing the troubleshooting measures we use here at Avista to diagnose problems, find solutions, and apply them on site. The example for this presentation is a municipal site that is using a well water source and has had a past history of biological fouling issues in their break tank. They started to see rises in delta pressure in the reverse osmosis system and an excessive cartridge filter replacement. Additionally, their high pH cleans for the membranes were no longer effective, and flows and DP were not returning to startup conditions. Now we'll focus on the system design. The water from the well first entered a green sand filter for the removal of metals. After the green sand filter, there was a chlorine injection, which combated the biofouling that the site had experienced in their break tank. After the break tank, there was an SBS injection to reduce the chlorine, protecting the RO from oxidation damage. After this was a cartridge filter, an anti-scalant injection to prevent scaling of the RO, then the high-pressure pump which fed the RO system. As increased delta pressure was observed in the first stage of the RO system, the site sent the first 3 elements from the first stage for individual performance testing at the Avista facility. This gave us a performance snapshot to determine which elements were most affected by the fouling problem. We see that the delta pressure is highest for the first element in their first stage, and as you travel through the system, the delta pressure becomes more manageable, even though it's still elevated. We expect delta pressure of clean elements to be between 3 and 5 psi. We'll also take a look at their flow. The flows were fairly consistent for the first 3 elements in their system, with about half of their original performance. Another thing we'll look at is the rejection. We'll note that the rejections are similar, but slightly below normal. So let's take a look at the first element from the first stage. We see the delta pressure is 19, the flow is 3.56 GPM, and the rejection is 98.9%. We selected this element because it's the worst performer. So if we can find a solution for this element, we can find a solution for the whole system. We reserve positions number 2 and 3 for full element cleaning, so we can take the solutions we find in the lab, apply them on a large scale to further prove their effectiveness. The first thing we do with our chosen element is check the weight on it. We found that it weighed 40 pounds, while new elements typically weigh 30 to 35 pounds. That's 5 extra pounds of mass inside of this element, blocking the channels and making it harder for water to pass through. We associate high weights like this with elevated delta pressures, which we saw during the single element wet test. This is our first piece of evidence that we're on the right track. Now we'll move on to our external inspection of the element. First, we'll take a look at the fiberglass casing. What we're looking for here is any mechanical damage, which might mean that the element has been exposed to pressure that's greater than the manufacturer's specification. We'll note that there is some mechanical damage with cracking of the fiberglass casing towards the concentrate end of the element. Additionally, we see foulant material coating the exterior of the casing, which means that water has been allowed to pass around the element. The most likely place that this would occur is at the brine seal. The brine seal is a chevron seal which seals between the element itself and the pressure vessel, making sure that all the water passes through the element rather than around. When we look at the brine seal here, we see that there is foulant material caught on the external side of the brine seal, which means that water flow has occurred on the exterior of the element. We'll then take a closer look at the anti-telescoping devices, or ATDs. The ATDs are here to ensure the mechanical integrity of the element. They prevent something called telescoping, where the internal mechanical components are pushed. Think of a paper towel roll that has been pushed from the center, creating a coning effect. When this occurs, it can be abrasive to the membrane surface in the presence of foulant material, but it also fundamentally changes the hydraulics of the element, making it harder to clean and recover. In this case, the ATDs are in good condition, however coated in orange-colored foulant. We'll then move on to more internal inspection. So we remove the anti-telescoping devices, and now we'll inspect the scroll ends of the element. If there is excessive foulant material on the scroll ends, it can create those high DPs that we see during wet testing by blocking the channels where water is supposed to flow through. An inspection of this scroll end reveals the presence of a thick layer of orange-colored foulant material, which is blocking some of that flow and creating the DP that we're seeing during the wet test. Now it's time for us to remove the fiberglass casing and look at the membrane surfaces. Now that we have the element enrolled, we can begin to inspect the internal mechanical components. First, we'll take a look at the feed spacers of the element. The feed spacers serve to separate the membrane leaves, allowing a channel for the feed water to flow through. They also keep the water flowing turbulently through the element, so it gives it kind of a self-cleaning effect. When foulant material becomes trapped within these feed spacers, it makes it more difficult for water to pass through the element. Since it's more difficult for the water, this creates a higher delta pressure across the membrane leaf. When we inspect these feed spacers, we see that there is foulant material coating the feed spacers, blocking some of these channels. That brings us to our active membrane surface. The components of the membrane leaf are two outwardly facing pieces of membrane held together by the glue lines. We'll inspect the glue lines to look for any damage which would cause a loss in permeate quality. In order to see the glue lines, we'll wipe away the foulant material and inspect to make sure that they are intact. These glue lines are intact, and that's what we would expect given our wet test results, as the rejection, although a little bit below normal, didn't suggest significant damage to the internal mechanical components. As we inspect the membrane surfaces, we see that they are slightly unevenly fouled. We have more foulant material deposited towards the feed end of the element compared to the concentrate. This is also a contributor to delta pressure during full element wet testing. Our next step is to inspect the permeate side of the membrane. We do this by cutting open a membrane leaf and looking at the membrane backing to see if we can find any obvious signs of contamination. We'll see that it is white in color and we don't see any obvious foulant material within the membrane leaf. We'll also perform acid testing, which tells us that there are metals present on the membrane surface. So we'll put a couple of drops of dilute hydrochloric acid on the foulant on the membrane surface, checking for effervescing or bubbling, which would mean carbonates, or a yellow color change like we see here, which means positive for the presence of metals. Now it's time for us to harvest samples from the full element to take into our lab for performance testing and cleaning studies. We'll want a sample from each unique area of fouling so that we get a full profile of the performance of this element. We have our samples, now let's head into the lab. When we ran our loss on ignition testing, we found that 72.7% of the foulant was inorganic in content. That means that the bulk of the foulant is inorganic. The client thought that they had a biological fouling issue, and that's what they geared their maintenance procedures towards. So now let's take a look under the microscope and see what biological material we can find. During the analysis, we saw mainly particles, which we associate with inorganics. Also, we saw amorphous inorganic material, which just means that it doesn't have a crystalline structure. For our organics, we found fungi. But the bulk of the analysis mostly revealed inorganics, which we expected from our loss on ignition testing. Our next step is to look at the foulant using Fourier transform infrared spectroscopy. During this analysis, unique peaks are seen which correspond to different functional groups. This analysis revealed the presence of iron peaks as well as calcium hydroxide peaks. No significant organic peaks were observed during this analysis, so we know that it's not one of their main phthalate. Energy dispersive X-ray analysis is the next tool that we use, and this really tells us exactly what we're seeing in the phthalate material. We get relative weight percentages of each element that's detected during this analysis. The sulfur weight percentage we see isn't contributed by the phthalate material. Rather, it's a part of the membrane materials. When we analyze new membranes, we typically see between 5 and 7 weight percentage of sulfur. If there's a phthalate layer present, it will mask that sulfur weight percentage, so we'll see much lower values. In this situation, we see only 0.95 relative weight percentage of sulfur. The sulfur weight percentage value is much lower because there's a thick layer of phthalate masking the membrane surface. What we can see through this analysis is that we have really high weight percentages of iron, first of all, with a little bit less presence of calcium. We saw the peaks for iron and also calcium hydroxide during our FTIR analysis, so this further gives us evidence that our main problems are inorganics and specifically iron and calcium. Now we want to take a really close look at the membrane surface and see the topography of the phthalate material. We'll look at the membrane using magnifications of 150x to 5000x. So we can really look at what's going on here. What we see is a layer of phthalate coating the membrane surface. The layer is thick, we can't see the membrane surface under it. However, it's cracked during the drying procedures associated with the analysis. This is characteristic of inorganics. Chromatic elemental imaging really ties all of our analysis together. Chromatic elemental imaging provides a spatial distribution of the elements within a phthalate layer. So we're seeing not only the topography of the phthalate, but the actual locations of each element within the phthalate layer. Let's look at the results for this analysis. We're seeing a high intensity of yellow. It's vibrant, it's bright, and this correlates to higher concentrations of the element iron throughout this phthalate material. We also see high concentrations of calcium in orange, isolated particles of silica, and also some of the organic fouling that the site had experienced previously. However, through chromatic elemental imaging, we're seeing the layering of this phthalate, so these organic patches are located above iron rather than below. So we'll know that we need to clean off this iron layer rather than focus on this organic material. Fujiwara testing is one of the ways we test for damage. Polyamide membranes are not compatible with chlorine. Fujiwara testing is a quick test. We cut up little pieces of the membrane, we place the test tube in a water bath, and we boil it. The reagents in contact with the membrane surface will cause the chlorine, if it's present, to break off of the membrane material, boiling through a secondary layer. For this analysis, we found a color change to a vibrant pink color you'll see here. This means that chlorine damage has occurred to the membrane surface. Through our testing so far, we've pinpointed what the issue is, and now we want to see how that applies to the flat sheet performance. So we take these samples over to our cell tester. This cell tester allows us to determine the individual performance of these flat sheet samples. We'll see that the flat sheet samples have lower than normal water passage and higher than normal salt passage. This is consistent with our full element results where we saw lower than normal flow and slightly lower than normal rejection. In these cell testers, we're able to trial many of our products. From this, we can determine what's going to be the best for removing our phthalate and also for restoring performance to these flat sheet samples. This is our first step in cleaner selection. You'll see here a time-lapse video taken over the course of an hour, which shows our product RowClean P903 removing all of the visual phthalate material. This product is now ready to try on the full elements. The site provided us with 3 elements. We chose 1 for autopsy, and we reserved the remaining 2 for full element cleaning. This gives us an opportunity to trial our product that we've chosen on a full element. When we cleaned these elements with RoClean P903 at 2% for 1 hour, we saw the delta pressures drop dramatically from 18 and 14 to 4. If you'll remember from the beginning of this presentation, we expect new clean elements to be performing between 3 and 5. So this element has been restored to its baseline performance. Additionally, the flows have increased from their original around half of normal to normal. We see that the rejections have improved. This was a successful clean. Based on the Fujiwara test results, the site adjusted their SBS injection to prevent further oxidation damage to the membranes. With the conclusions of the autopsy, one of our application specialists went on site and was able to trace the source of iron to the green sand filters, which were not properly maintained. To make problems worse, the chlorine addition after the green sand filter was inadvertently oxidizing dissolved metals that were not being removed by the filter. The green sand filters were regenerated, and regular monitoring of iron concentration out of the green sand filters was established. In addition to solving the bypass issue, the elements were cleaned with RoClean P903, a single low pH cleaner. This restored the system to baseline performance, including dropping delta pressures by 10 psi per element. Post-clean, the site was able to return to their normal maintenance procedures. The key takeaway is that the autopsy provided us with invaluable information. Without it, the site would have continued to misdiagnose their issue as biological fouling rather than iron. The site is now back up and running, and we are pleased to say that iron is no longer a fouling concern. Thank you for watching. For more information, please visit avistatech.com.